In a recent series of videos I was working on a 486 based system. It was a controller for a CNC machine, and as a result of some of the questions I got, I thought it might be interesting just to go over some of the basics of how I got into this type of work and what first got me involved with this. And so this is probably not for everyone that's subscribed to my channel. This is more about how I went through initial development of my own PC systems, rather than a lot of detailed repair work. There will be some repair work in this, it's inevitable with this type of thing, but I want to cover some of the fundamentals that I learnt when I first started getting into working on computer systems. And initially I was working for a company that developed high-end optical equipment, and part of that was they had big machines that had embedded microcontrol systems, and the very early ones had 4004s, although I was never involved in the development of those, but I did get into the 8008 type era when I first started working on them. Never owned one. It was high-end machines that we sold. But in that process I got to know embedded systems fairly well and got very interested in them, and ultimately I started collecting and picking up bits and pieces of PCs. This is back in the early 80s, and that's when these things were just starting to become available, and early on they were fairly unreliable. They weren't too bad, but it meant that quite a few of the boards, if you knew where to look, you could find them relatively cheap. And this is back when I had absolutely no money at all. I couldn't afford to buy ICs or parts or anything, so it was down to the kindness of people I knew, friends that worked with companies. I had one friend in particular that worked for a company, and they had a department that tried to repair this sort of thing. So I started being given bits and pieces. The first thing I got was actually a 5170 case. Now unfortunately I've disposed of a lot of this many years ago, much to my regret, but I got this 5170 case, and this is back when they were fairly new, so it was in really nice condition and it was quite interesting. Didn't have a power supply, but had all the brackets in, didn't have a hard disk. Had some of the internal bracketry as well, but other than that it was just an empty case. But I still accepted it anyway. It was quite interesting, quite nice to look at. It did have the LED and key panel, and the key as well, which was going to be quite useful later on. I actually showed a picture of this machine some time ago. In fact, this is the picture I showed. And I said at the time when I showed this picture that it was a 5150, and someone corrected me, probably understandably, and said no, that's a 5170, which the case was a 5170, but it actually had a 5150 motherboard in it, which for me means it was a 5150. And at that point I picked up the 5150 motherboard. None of it worked when I got it. All the things I picked up were faulty, which is why I ended up being given them. And it also allowed me to learn a great deal about how the systems work. Now bear in mind, this was long before the internet existed, so you couldn't just Google how to fix the things or looking for data sheets. You had to actually buy data sheets back then, and they were expensive, and I couldn't afford them, so I had to reverse engineer most of it. And you can learn a huge amount doing that, and I do highly recommend that anyone that's interested in a career in developing systems, electronic systems, computer systems in particular, this would be a very good learning exercise. It's not really applicable technology, but the general principles absolutely are, and even in modern Windows systems there's a huge amount you can learn from playing with a system like this. But what I ended up with in the 5150 system was just a floppy disk, which again I had to repair, and a friend gave me a copy of DOS, which I proceeded to try and install, but it wouldn't work. I managed to get a video card from somewhere. I can't remember where most of it came from. I was then given two AT power supplies that would of course bolt into the 5170 case, but neither one of them worked. Both had the same fault, as it turned out. There's a small round bridge rectifier in there that was mounted kind of upside down on a PCB, and it used to get really hot and desolder itself and then just fall out of the board. And when I picked up the power supplies, they both rattled. So first time I'd seen one, opened it up, found this thing inside and thought, that's a bit strange. I assumed at first that because it had come from a repair department, that the repair engineer had desoldered it, left it inside, and decided not to go ahead with the repair. But when I tested the bridge rectifier, it seemed to work, so I soldered it back in and the power supply came back to life. And I did it with a second one and that also came back to life. So I now had a motherboard, a floppy drive and a power supply. So the next thing was a keyboard. Picked up a keyboard. It was an AT keyboard, but obviously I effectively had an XT machine. So it did actually work. I plugged it in, and although the AT keyboard is a bidirectional keyboard and the XT isn't, it still worked, but albeit in the limited way that the 5150 was trying to drive it, but it did respond correctly to key presses. So I started putting all this together. After about a month and a half, I finally managed to get the 5150 to work, and I started trying to install DOS and get that working. Managed to pick up a monitor, and it was a 9-inch monitor. 9 inch, not 19, just 9, and it had orange phosphor, so it was quite a strange little monitor, but it was fairly easy to repair. Just had a broken wire inside, fixed that, and now I had a machine that would show me some text on the screen, which was quite exciting. Didn't have a hard disk, but I could kind of boot to floppy. Didn't really work properly, but I was going through figuring out what was wrong with it, getting it to work. And about that time, the friend that gave me the 5170 case gave me 2 of these motherboards. Neither one worked. This is one of them. The other one is the one I used for several years, but unfortunately, as I say, I think I've disposed of that. I can't find it anywhere, so I think I must have thrown it away. Again, much to my regret. It was version 1 boards. They were identical boards, seemed to be made from the same in the same batch, and both had numerous faults. The other one I repaired, and again learnt a great deal doing that. It was actually one that had the 4-ROM BIOS chipset. The 2-ROM BIOS chipsets, identical code, it's just been split differently, and you can use either 2 256K ROMs or 4 128K ROMs, and the only thing you need to change to do that is there's a jumper over here, and all you do is it's in a socket, just pull it out, turn it around 180 degrees, plug it back in, and you can switch between 256K and 128K ROMs. As you can see here, I've got 2 newer ROMs fitted. The ones that were in the original board were mask ROMs, so you couldn't reprogram them. But I did actually replace them. In fact, I spent a lot of time with that board making up my own BIOS systems. I actually used the board for a while like a huge microcontroller. Didn't use most of the board, of course, but you could use it as a glorified microcontroller and learn a huge amount about programming Intel devices doing that. This is of course an 80286. I do have the 8087 code processor. It's not plugged into this board at the moment, but I do have one. But what I've done with this board is plug in 2 256K ROMs that have a later BIOS in them, and this BIOS contains the CMOS configuration. In the original BIOS, the CMOS configuration was done using a floppy disk, and I'll show that in a later video as I go through this process. But I've got this configured because I've been trying to repair this board. Had it for over 40 years and thought I'd show this as part of this series. Might switch to a 486 later in this series just so it moves along a bit more smoothly, but I thought I'd show this and try and get this working so you can see kind of what we're up against back then trying to get these systems working. And again, as we go through this, bear in mind there was no internet, so the information was very hard to come by, and most of it you had to figure out yourself by reverse engineering the board. So what I'll do now is, I've been repairing this, I've got it now pretty much repaired. A couple of failed ICs. I'm not sure if they failed over the last 40 years or if they were part of the original fault. But most of the problems I had with this were related to failed memory devices. And that's what I want to cover really in the remainder of this particular video. In that, if you've ever seen one of these boards, we have this strange arrangement where we've got these piggybacked DRAMs. And I've seen a lot of weird and wonderful theories as to why IBM did this, from redundancy, so if one chip failed, the other one took over, which isn't the case. If one of these fails, you lose the entire bank of RAM, and if it's a lower chip, you then lose all the subsequent banks as well, so it's not due to redundancy. I saw a theory that it was down to yield rate on the 128 devices, so they used half of a device on the top, half of another device on the bottom, and disabled the other half, so they're really 128K devices. This is 128 by 1, by the way, in the way it's configured as a package. Now, I don't believe that's the case either. I did X-ray some of these a few years ago, and they all contained nothing more than a 64K device. But I want to go over how these are physically arranged, and then what you can do to replace these if you can't find any. Now, you can find these on eBay, but there is a workaround. If you don't want to wait for delivery and you have some 64K DRAMs knocking about, which is the way I repair them. I do have some spares of these, but quite often I'll make up a replacement package using two 64K DRAMs. Very easy to do. But before I do that, I thought I would go over how these are configured and why I believe IBM did this. So the first thing, let's get rid of these. So the first thing we'll look at is the schematic for this, and it's really, I think, fundamental to why IBM took this particular route. So if we examine the schematic for the DRAM part of this board, we've got two pages that cover the stacked DRAM. 64K, each of these is a 64K by 1 bit package. And these do include parity checking, so there are actually 9 bits effectively per bank. And although this is identified as a 256K or 512K board, that's bytes, whereas it's a 16-bit machine, so it's not 512K words, it's 512K bytes, which explains why we have this arrangement and doesn't seem to make sense. You wouldn't find, for example, 512K words in this. But if we look at this, you'll see that we have a fairly typical looking arrangement for DRAM. Now, if you've read my book on designing a Z80 computer system or seen the videos I've posted on how the DRAMs work, then you'll notice that if this was just a 16-pin DRAM, you might wonder how we can address 64K using just 16 pins, because you'd need 16 bits to address 64K. So it's done as two 8-bit bytes. So what you do to address one of these and select a particular memory location in them is you put the row address line onto the address pins, the 8 address pins. So it's obviously just an 8-bit byte. And then you assert the row address strobe or the RAS line. And when you've done that, you then change the address that you're feeding in to the address lines to the column address that you want to use, and then you assert the CAS or column address strobe. And at that point the device will respond and it will output the current bit you selected onto the output pin. These all support what's called early write, and that mechanism, I won't go into that in detail now, but it's a mechanism that allows you to connect the output pin to the input pin. It saves on complexity of the external circuitry. Now, The advantage in doing it like this and retaining an 8-bit device rather than going to, when I say 8 bits I'm talking about address lines, rather than going to 9 bits, which you would need if you went to a true 128K DRAM. Obviously you'd need a 9-bit address rather than 8-bit. The disadvantage in doing that is all the support devices that typically you use in a system like this, especially back in this era, were 8-bit devices. So the buffers were 8-bit, the decoders were 8-bit. So if you went to a 9-bit address system, you would massively increase the complexity of the board, because just for the extra bit you might have double up the number of devices used in the decoders and the buffering, etc. But doing it the way IBM did it meant that they could retain the 8-bit addressing of these, and they effectively just created 2 RAS lines on the package. This can be looked at as a single IC now, but with 2 RAS lines, and because the sequence is a RAS, CAS, and then the output, if you don't do the RAS and you just throw the CAS, it doesn't do anything, the chip ignores that. So you have to go through the entire sequence before the chip will respond. And by having one of the RAS lines go to the top chip and the other RAS line going to the bottom chip, then you could effectively address the top or the bottom chip independently using common address lines. In fact, all the pins are common apart from one of them, which we'll now have a look at, and I'll show you how that's arranged. But I believe the reason they did this was to keep the board reasonably small, because if you double the number of devices, of course, if you wanted to use 64K devices, you'd end up with a much bigger board because of the space that these devices take up. But by stacking them like this, you could keep the board fairly small, and you could also keep the board even smaller by not having to have 9-bit addressing. So the question is, how did IBM actually do this? So how did they manage to stack devices like this without and still be able to independently access the top and bottom devices? And the way they went about it is surprisingly simple. So this is how they stack the devices. You can see that all the pins are commoned, so that's just straight up and down through both devices, and that means that the top and bottom devices are not the same. So if we look at the spec sheet for a typical 64K DRAM, which is what these actually are, you'll see that we have the usual pins, the 8 address lines, the output, the input, the write line, and a single RAS line and a single CAS line, and then the power supply. And interestingly, and what makes this possible, is we have one of the pins that's not used, so pin 1's not connected. If we now look at the package here that's designated as a 41128, which is what we have written on the device, then you'll see that the pin outs are very similar. In fact, if we look at the right hand column, you'll see that all the pins are actually identical, exactly the same designations, and on the other side you'll see that the only ones that vary are pins 1 through 4, and even then pin 4 on either top or bottom, depending on how you view it, could be the same. So what IBM did is they changed the way that they effectively bonded out the devices. So if you're not familiar with the way that ICs are made, if we look inside a typical device, and with the windowed EEPROM, that's quite easy to do. So under the microscope, if we look at this image, you'll see a number of fine gold wires running from the actual device itself. That's a small square in the center. So these little gold wires are running out to what is called the lead frame. And if we look at some diagrams, I've got some diagrams printed here. So the lead frame, when it's first made, looks like this. They're etched, and the way the ICs are manufactured is the actual silicon wafer, which is very small, is bonded to the little square in the center, and then the pads that are on that for external connections are bonded using very thin gold wires between the chip itself and these leads. And then when the bonding is done, it's encapsulated in the black epoxy that you normally see. The pins are, all the bits that's not required are chopped off, and then the pins are bent over, and we end up with the devices that we're all familiar with seeing. And so if we look at that in cross section, you end up with something like this. So you've got the chip, the carrier, and then the small wires, and then it's all encapsulated. And a representation of that would be something like this. You can just see we've got the chip in the center, the thin gold wires going out to the leads themselves. And that means that what IBM can do if they want to is mess about with the way that these connections are made. And in fact, I've just drawn up the way they actually did it. So very simple. The top device, the two devices are identical. It's exactly the same. They're both 64K DRAMs, but all they did is on the RAS line, single RAS line, there isn't a double RAS line on these because they're standard devices. But what they did to make up these packages is on the top IC that's in this stacked package, they bonded the RAS line to pin 4, and pin 3 wasn't connected, so that non-connected pin has been moved from pin 1 to pin 3 in this case. And on the bottom device, that RAS line was bonded to pin 3, and pin 4 was left non-connected. So you had two slightly different devices, and all they had to do was modify where that particular thin gold wire was bonded to on the lead carrier. And that meant that when you stack them, you end up with two RAS lines. And if we look back at the spec sheet, excuse the writing on here, I couldn't find one that didn't have that on. But what we have is pins 3 and 4 are labelled as RAS 1 and RAS 2. And depending on which one you assert during the process of reading or writing the package, it will determine whether you access the top or the bottom chip. And that means that the only extra decoding you need on your main board is to determine which of these two pins, so you can treat it like an address line. And that means that all you have to do is use effectively address line 8, or however you're mapping this, one single address line to decode the entire package in the same way that you would if these two lines were address lines. So it works really well. I believe that's the reason they did this. It was just because it made it much more efficient to design the rest of the board, and that you didn't need to do any 9-bit decoding or additional decoding for the device. You just decode the device like it's an 8-bit and treat it like it's got an extra 2 banks. Okay, so that comes on to what I mentioned earlier. If you need to repair one of these, how can you go about doing that? So I'll move the camera and point it at the monitor we've got here. So I've got on this board at the moment is a video card, power supply, and it's hooked up to this monitor. So I'll just move the camera. Okay, so although I've repaired this board already, I have put one of the faulty devices back into it, so you can see the effect you'll get when you boot it up. So I'll power this up, and it will go through its normal post-test, and one of the first things it does is check the amount of RAM, and hopefully you can see it's reporting 128K of RAM. So I'll turn it back off. So I'll just move the camera down a little bit. So this little blue jumper here is used to select 256K or 512K, depending on whether you have the second bank of RAM installed. It's currently in a 256K position. I'm going to move it to the 512. And because this has got a second bank in, you'd expect that to make a difference, but move the camera back up. Boot the system back up, so it'll go through its self-test again. Hopefully you can see what it's actually saying on the screen. but it's still reporting 128k of RAM. So I'll turn it back off. So the reason it's doing that is because on this corner device the top chip is faulty. So it's going through, it's starting to do the cell test. It's tested the first bank of RAM, which is the bottom bank of RAM. It's then found 128k, which is what it should find. It's then come up and it's starting to test the effectively next bank, which is the top layer of these 16 devices. And the top one's faulty, so it's failing the test, and then it doesn't test anything beyond that. So this top 256k of RAM is being ignored. What I'll do now is I'll change this and I'll put a device in that is faulty. Both top and bottom devices faulty, and you'll see the difference. Okay, so we'll power that up. And now you can hear, hopefully, the machine beeping. Raise the camera, and there is nothing on the screen. So that beeping is a post error message, which basically says there is no usable RAM fitted to this machine. And that's because it's testing the first bank, finding that there is no usable RAM there, and it's just ignoring the rest of it. And it will do that if just the bottom chip in the package is faulty. All the rest of the devices will be ignored. So I'll turn this back off. So if you want to make up a replacement, it's very easy to do. So you just get two 64k DRAMs, you stack them, and on pins 9 up through 16, you just solder them directly together, as I've done here. The other side's a bit more complex, it looks a bit messy, but normally I would put some epoxy over this, but I've left this open so you can see it. So all you do is on the bottom device, you leave pin 4 straight down and out, and that's your second RAS line. The top one is the first RAS, and that has to go to pin 3 position, so you just bring it across and down. The pin that is normally here you have to bring across to the left, because both the remaining pins need to be moved to the left one position, but they are in parallel, so the top and bottom pins are connected together, as are the second pins. So they're just brought across, and you can see that all we've done here is ignore the non-connected pin, and although we're soldering this pin to this one, remember that this pin on the bottom one is not connected internally, so this is we're just using this as a kind of a pin for us to plug in. And then the second pin here, I don't know if you can see it, it's just folded back on itself and soldered to the top pin. Same with the next one, it's just folded back and soldered to the top one, rolled across, and that's all you need to do. So we'll plug this in and see if it solves our problem. So I've got our replacement device plugged in, and we'll move the camera, power it up, and see if we've resolved the issue. Okay, well hopefully you can see that. It's reporting now we've got 512k of RAM. So all the RAM is now working, and so that's just using a couple of 64k DRAMs. You don't need the special stacked RAMs, but as I said, this is kind of my theory as to why they did this. I can't guarantee that's correct, but it does seem to make the most sense. Now in the next video in this series, we'll look at trying to hook up the various devices. Also we've got a floppy disk and hard disk controller failure, mainly because there aren't any there. So in the next video in this series, we'll try to deal with those errors, try and get the system up to the point where we can think about installing an operating system, and then we'll go through how I proceeded beyond that point. But this is really mirroring what I did back in the 1980s when I first started working on these. It was just working through trying to get the machine up and running, trying to figure out why it wasn't working. As I say, it was much more difficult back then, and trying to get hold of the various bits and pieces I needed wasn't always easy, but I'll try and cover that as we go through. And although this won't be a full tutorial on how to program the Intel devices, I will touch on it a little bit as we get into the assemblers and compilers that I used back then, and hopefully you may find it of some interest.